Hey guys, in today's video we're going to be looking at Chapter 9, Learning Objective 2 within Lecture 20. So we're going to be looking at molecular polarity, so whether or not a molecule is polar or not. We're going to be basing this on bond polarity and on our VSEPR theory, so make sure that you understand VSEPR before you get into this video. So as a note, let's remember what bond polarity is. So bond polarity is when we have a bond that is polar. And in order to have a polar bond, we have to have a distribution of electron density. In order to get a distribution of electron density within a bond, we have to have an electronegativity difference that is greater than 0.4. So the two atoms that are part of the bond will have to have a greater than 0.4 electronegativity difference. And this is going to be 0.4 on the Pauling scale. Okay, so when we have a bond dipole, we show that using a dipole arrow. And a dipole arrow is very similar to a vector. It is going to have direction and magnitude. We are showing the direction of the electron density shift. So it's a little bit different than an actual vector. An actual vector is going to be pointing in the positive direction, while a bond dipole is going to be pointing in the negative direction. So the arrow of the bond dipole will point towards the area of greater electron density. Okay, so when we have a bond dipole and it's pointing in a particular direction, if that is not canceled out by other bond dipoles within the molecule, we can have a polar molecule, a molecule that has an overall molecular dipole. So if the bond dipole is not canceled out by another or other bond dipole, then the molecule will have an overall molecular dipole. Okay, so it's going to have a direction of polarity within our molecule. We can cancel it out. We can cancel out a bond dipole by having an equal magnitude bond dipole in the opposite direction. So what we find is we will have a molecular dipole if we have asymmetry, or we will have no molecular dipole if we have symmetry. So molecular dipoles will exist if these two conditions are met. Of course, first, you have to have bond dipoles. Okay, so obviously the first thing is we have to have bond dipoles. Second, we have to have asymmetry. I don't think I spelled that right. Let's try that again. Asymmetry. Asymmetry about the molecule. So it has to be a molecule that is asymmetric or lacks symmetry. So, polarity is when we have a molecular dipole. So a molecule is polar if we have a molecular dipole. So, to be polar, it means it has poles. We can think about this kind of like a magnet. A magnet has a positive pole and a negative pole. That is the same thing that a molecule that is polar has. It has an area of positive, area of negative. So part of the molecule is positive, part of the molecule is negative, and it's partial charges, right? So we're talking about molecules. We're not really talking about ions in this case. So we have, in the case of a polar molecule, there is an area with a partial positive charge, and there's an area with a partial negative charge. So generally, again, we're not looking at full charges here. Okay, so how do we know if we have a polar molecule? Well, I have put a flowchart on your worksheet, but I want you guys to try going through. I'm going to go through the flowchart real quick. So first, the first question is, does a molecule contain polar bonds? So for a molecule to be polar, it has to have polar bonds. So if the molecule contains polar bonds, we have a possibility that it will be polar, but not necessarily. Okay, so first it has to have polar bonds. If it has polar bonds, then it could be polar. If it does not contain any polar bonds, it doesn't matter. If the answer is no, it does not contain polar bonds, the molecule will be nonpolar. But if the answer is yes, then we have to look and see if the molecule has symmetry or asymmetry. Symmetry means that it's going to be polar, or sorry, symmetry means it's going to be nonpolar, asymmetry, polar. So next is the shape symmetric in all three directions. So this is when we start to bring VSEPR into this. There are several different symmetries or several different molecular geometries that are going to be considered symmetric molecular geometries. So our symmetric molecular geometries are going to be our linear geometry, linear molecular geometry, trigonoplanar molecular geometry, tetrahedral molecular geometry, trigonal bipyramidal molecular geometry, octahedral molecular geometry, and square planar molecular geometry. So these will be our symmetric geometries. So if the answer is yes, it has to be one of those symmetric geometries. If the answer is no, it's going to be one of these geometries. So our asymmetric geometries include bent, trigonal pyramidal, molecular geometry, obviously, seesaw or sawhorse molecular geometry, T-shaped molecular geometry, or square pyramidal. Molecular geometry. So these are all molecular geometries that have lone pairs around their central atom. There are a few in here that always have lone pairs as well, but still symmetric, like square planar. Square planar has two lone pairs around the central atom, but they're 180 degrees from each other, so we still have a symmetric shape. Linear can also be one of those molecular geometries that have lone pairs around the central atom. If we're talking about linear in the terms of our trigonal bipyramidal or linear in the terms of octahedral, both of those have lone pairs around the central atom, but they are still considered linear molecular geometries. I do not include in this if we have two atoms in a line. We have to have all three atoms in that linear shape. So something like carbon monoxide would not be included in this linear shape. Okay, so if we are symmetric in all three directions, we have to think further. But if we are not, then it is polar. So if we are asymmetric, then we have a polar molecule. If we are symmetric, if we have a symmetric molecular geometry, then we have to determine if we have actual symmetry within our molecule. So the next question is, are all the peripheral atoms surrounding the central atom the same? Okay, so if all the peripheral atoms surrounding the central atom are the same, then we maintain that symmetry and we have a nonpolar molecule. If, however, we do not have the same atoms around our central atom, what's going to happen is we're going to have an asymmetric component to our molecule. And since we have asymmetry plus polar bonds, we'll have a polar molecule. Okay, so some things to note about polar molecules is one, polar molecules are going to have different properties than our non-polar counterparts. So, polar molecules contain a partial positive and a partial negative area. So they contain partial charges. So positives and negatives, we know from our electrostatic potential energy, positives and negatives want to get together. And the greater those partial positives and negatives, the greater our molecules are going to hold on to each other. So greater partial charges, greater hold between molecules. So what does that mean? If molecules are being held closer together, tighter together, then they are going to be harder to pull apart. That's going to lead to structures that are going to be harder to melt, harder to boil. So polar molecules have higher boiling points and melting points versus nonpolar molecules of the same size. They are also going to interact with each other. Polar molecules will interact with other polar molecules because they all have partial charges. But polar molecules and nonpolar molecules are not going to interact very much. So we would say that polar molecules can dissolve in other polar molecules, while nonpolar molecules will not dissolve in with polar molecules. So they will have different solubilities. Generally, ionic compounds will dissolve in water. Ionic compounds will dissolve in polar substances. We talked about exceptions to this, but that's only if the electrostatic interactions between the ions are so great that we don't pull them apart. But they're usually soluble in polar compounds. Okay, and then polar compounds are usually soluble in polar compounds. And then nonpolar compounds are by themselves. They don't solubilize ionic or polar compounds, and they also aren't soluble in ionic or polar compounds. So nonpolar molecules don't dissolve in polar compounds. And polar and ionic compounds do not dissolve in nonpolar substances. Okay, so overall, they are a dissimilar species because nonpolar compounds don't contain partial charges, so they're not going to interact with things that do have partial charges. So we always think about a like dissolves like mentality. So things with charges dissolve other things with charges, things without charges dissolve other things without charges. So Let's look at what I mean by these partial charges. We're going to look at two compounds, water and carbon dioxide. Okay, so water is a polar compound. It is like the poster child for polar compounds. And if we were to draw out bond dipoles, we'd see that there's a bond dipole here, bond dipole here. So we have an area of negative charge here, an area of positive charge here. So we produce that dipole. Look over at carbon dioxide. We have two bond dipoles. They are in equal but opposite directions. So when we do our negative areas, we have a negative area here, negative area here, then we have a positive area here, but they average to the same place. Our negative area is going to average in the center. Our positive area is going to average in the center, so they will cancel each other out. So the bond dipoles. Now, if we look at water versus carbon dioxide, hopefully you know that water is a liquid at room temperature. And then carbon dioxide is a gas at room temperature. And this is very much because of those partial charges. So water molecules are going to like other water molecules and they're going to stick together because of those charges. Carbon dioxide molecules don't care about other carbon dioxide molecules because there's no charges that they can stick onto, so they just kind of float by themselves. So very different physical properties when we think about a polar substance versus a non-polar substance. And as I said, water is usually our poster boy for our polar compound. And we usually think about oil or oils being our poster boy for non-polar compounds. So that whole like dissolves like, if you ever tried to put water and oil together, they don't mix because they're very dissimilar substances, because water is polar and oil is non-polar. That is everything for this. I'll see you guys later. Bye.